So guys, welcome to this session. In this lecture, we are going to learn. In this lecture, we are going to learn microstructure. Microstructure of eutectoid steel. As we have learned in our previous lecture, that eutectoid steel is the main center of attraction for our analysis, so that I can control the properties in steel. Okay, so now just let's try to recapitulate how eutectoid point looks like. So this is what temperature in degrees Celsius. This is weight percentage of carbon, right? And here we have gamma phase, here we have gamma phase, here we have alpha phase. This is at temperature 725 degrees Celsius. This point is located at 920 degrees Celsius. Okay, so this phase is gamma, and here it is alpha, and here this side Fe3C was there, right? So can you tell me what is the name of this phase? This will be alpha plus gamma. This will be what? Gamma plus Fe3C. This will be what? Alpha plus Fe3C. Okay, and this point is called, this point, we call this point as eutectoid point. We call this point as eutectoid point. Okay, now let's see what was happening at eutectoid point. Eutectoid reaction. So you can see here what is happening. Gamma is cooling into alpha plus Fe3C, alpha plus Fe3C at 725 degrees Celsius. Okay, so this is the okay, this point is what is the concentration of carbon here. This is 0.8. This point is having 0.02, 0.02. Okay, and this reason after the 0.8 weight percentage, this is called hyper eutectoid region, and the region before 0.8% is called hypo eutectoid region. Okay, so these are two reasons, and these are the eutectic reaction which is happening at eutectic points. Okay, now let's try to explore what is the microstructure evolution when the gamma austenite cools at this particular concentration and it comes to this region. Okay, now we will do it in another slide. So now let's draw this again. This is gamma, this is alpha plus gamma, this is alpha, this is alpha plus Fe3C, this region was Fe3C, right? This will be what? Gamma plus Fe3C. Okay, this is temperature, this is carbon weight percent. Okay, fine. Now let's fix the concentration for 0.8 weight percent, and let's take 2 point A here, point B here, right, at same concentration. Okay, so this 0.8 is called what? Eutectoid point, and we have seen that what is the eutectoid point reaction. We have, I think, no need to write here, we have write it many times. So here at 0.8 gamma will convert it into what? Alpha plus Fe3C. Now let's draw the microstructure for point A. Okay, so point A, it is what? It is present in austenite region. Gamma means austenite, right? So it is present in austenite region. So let's try to draw microstructure here. So guys, just listen this rule. Just draw these three pizza pieces, right? First draw one circle and just draw these uh, three pieces of pizza, and just draw the vertical and horizontal lines. These are just the virtual representation, or called cartoon, of real grain structure, real microstructure, right? This will be okay. So this region is called greens. These lines are called grain boundary. Okay, and all these regions are, this is all what? Gamma. All these regions are gamma. No, the right. write it here. This is gamma. So you can see here we will get a polycrystalline single phase gamma. Here we will get polycrystalline single phase gamma. So what is the meaning of polycrystalline? You can see here these grains are oriented these differently. So polycrystalline means differently oriented grains. Okay, so this is what microstructure for uh, point A. Now let's explore what is happening at point B. Point B is present in this zone, which consists two phase alpha and Fe3C. Now let's try to draw this circle again. Draw this circle, and what is our step? First, make it in three, cut it in three pieces, जैसा कि पिज़्ज़ा में कटा हुआ रहता है. Okay, and what we have to do, just draw a layer. This will be alternate layer of alternate layer of alternate layer of alpha and Fe3C, alternate layers of alpha and Fe3C we will get here. Okay, so and here this yellow color, I am putting this yellow color just to differentiate the two lamella. and this is green boundary. This is green boundary. Okay, so you can see from this region, this red color I am denoting it by alpha. This is denoted by alpha iron, and the yellow color we are denoted it by Fe3C region. This is Fe3C region, and this, the combination of alpha plus Fe3C, this is known as perlite. Perlite is it means that it looks like pearl. It looks like mother of pearl. It is nacre, Nacre. If you search nacre structure on Google, you will find alternate layers of hard and soft phase, right? So because here we are getting alternate layers of alpha and Fe3C, that's why we are calling this as a perlite, right? So here perlite. Now some important observation. So you can see perlite consists two phases, alpha and Fe3C. Now if someone is asking you, can you tell me what is perlite phase? So the question is itself wrong, because perlite is not a phase. Perlite is not a single phase. Perlite is microconstituents. Perlite is Perlite is microconstituents. That is, this is mixture of two phases. That is mixture of two phases, which is alpha plus Fe3C. Another point, perlite is PAR. Perlite is not a single phase. Perlite is not a single phase, right? And here what we are getting, here in perlite we get an alternate layers of alpha and Fe3C, and these layers are oriented differently. These layers are oriented differently in different regions. And these different regions are called as colonies. You can see here that here it is oriented like this, here it is oriented like this, here it is oriented differently. So these are called as colonies. So this is all about microstructure evolution. For eutectoid steel. Now let's try to explore how the microstructure looks like for hypoeutectoid steel and hypereutectoid steel. Let's try to explore this. So come to this page. Let's draw the eutectoid region again. this is temperature, this is carbon weight percentage. We have drawn it like this. Okay, so this temperature was 725, this temperature is 910. And this is what gamma, this is alpha, this is alpha plus gamma, and this is alpha plus Fe3C. Okay, and this is what gamma plus Fe3C, this is gamma plus Fe3C. Now let's try to draw 4 points in hypoeutectoid region. Okay, it will be at the same composition. So this is point A, one point is here point B, one point is here point C, one point is here point D. Okay, so now let's take 4 point at different location in hypoeutectoid region, and this is what 0.8 weight percentage, and this region below this is called what? Hypoeutectoid region. Okay, so let's draw for point A how the microstructures look like. So this will be point A is present in gamma, which is gamma austenite. Okay, so here we will get similar as we have obtained earlier. So just draw one circle. Okay, and draw the circle and divide it in 3 equal parts. Okay, three equal parts. So this will be these are grains. Its orientation are different in different regions. So this is what? This is gamma austenite. So this is grain boundary. I'm just making this dark. Okay, so here we get gamma. Gamma is what? Single phase. single phase austenite as we have learned earlier. This is what polycrystalline gamma, right? You can see these crystals are oriented different in different grain boundary, in different grains. So this is what gamma austenite. These lines are grain boundary, these are grains, these are grain boundary. Right now, let's see what is happening at point B. Point B, this point is present in two phase region. Okay, now let's draw the microstructure for this. So first draw a circle of and divide it in 3 equal parts. Okay, and just draw the austenite phase first. Okay, so this will be grain boundary. And just draw these vertical lines. Right now you can see this is present in two phase region. Now what is going to observe in its microstructure, that there will be some nucleation will start at the grain boundaries. At the grain boundaries, so we call this phase, as alpha dash, and this region we have already discussed earlier. This region is gamma. So this alpha dash is heterogeneous nucleation because this is, you can see, this nucleation is happening at different location, at different concentration. That intensity will be different at different regions, right? This will be what heterogeneous nucleation. That is, what is the meaning of heterogeneous nucleation? That is a new phase form at grain boundary because these grain boundaries are having very high surface energy. So this is the primary reason where the heterogeneous location this is the primary reason where the heterogeneous location nucleation will start, and it will form a phase that is called alpha dash. Okay, so here you can see that in two phase region we have alpha and gamma. So here we are naming this phase as alpha dash because we have represented alpha with this, so that's why we are representing it by alpha dash. Now let's try to see what is happening at point C A B. Now let's see what is happening at point C. So the point C is so point C is just above the it is just above this eutectoid point. Point C is just above eutectoid point. Now what we get here, so let's draw it nicely. So here we will get some interesting observation. Okay, for draw one triangle like this, then another triangle like this, then another triangle like this. Okay, so this is what here at point B nucleation has just started, and at point C this nucleation has grown bigger at the grain boundary region, right? So this is called alpha dash. This is alpha dash. This is called pro-eutectoid ferrite. Pro-eutectoid ferrite. This is called pro-eutectoid ferrite. Why? Because this phase is formed just before eutectoid point, right? Just before eutectoid point. That is why this is called pro-eutectoid ferrite, right? This is pro-eutectoid ferrite in hypoeutectoid steel. Okay, so this is the microstructure present at point C. Okay, so the remaining region will be same as above. This will be what gamma austenite. This is gamma, right? This is for point C. Now let's draw this for point D. Now let's draw this for point D. point D is again, this is present in two phase region. This is present in two phase region. Okay, now let's try to draw the microstructure for this point. So just first draw one circle. Okay, good. And just draw the center, and it will be what, just extension of this curve. So first draw three regions. Okay, these regions will be what, alpha dash. Now what is happening here, that nucleation has started at point B. Now it will grow slowly as we come to point D. Okay, so this is called alpha dash. What we have named it, this is named as pro-eutectoid steel. Okay, and this region we came in Fe3C region. Okay, so just draw this. I'm drawing this with different color to make it, to make a clear distinction between the phases. Okay, so you can see we came to this region alpha plus Fe3C. Okay, so here we will get alternate lamella of, this is what, this is Fe3C, and we will get here alternate layer of F alpha and Fe3C. Okay, so this will be what, Fe3C, and this yellow color region will be what, alpha. This will be alpha, Okay, now here you can see this alpha dash is what? Proeutectoid ferrite. This we will write as proeutectoid proeutectoid ferrite, and this is what? This is alpha. And so the combination of this alpha plus Fe3C, we will call this as perlite. We will call this as a perlite. And so you can see here that at point D we will get what? Combination of alpha dash. We will get combination of alpha dash plus this perlite. Okay, so you can see at point D at point D at point D we will get combination of alpha dash and perlite, right? So this is microstructure of hypoeutectoid steel. Now in similar manner we will explore the microstructure for hypereutectoid steel. So let's explore this quickly. So we will draw the same diagram so that we can understand it properly. So this is what gamma, this is alpha plus L, and here we will gamma plus Fe3C. This region is Fe3C, and this will be alpha plus Fe3C. Okay, now let's take 4 point here, A, B. These will be on vertical axis. A, B, B, C is here, and C is just above this eutectoid line, C, and this is what? D. Okay, so now let's try to make microstructure for point A. So you can see this is the austenite region, so we will get the similar microstructure as we discussed earlier. Draw a circle, cut it in 3 parts, and just draw the horizontal and vertical lines. These are the differently oriented crystals which forms grain. Okay, so this is simple. We have already discussed. This is gamma. These are grain boundaries. These are grain boundaries. These are grains. Grains are differently oriented crystals. Okay, now let's look into point B. Okay, so just draw this circle. Point B, it is present in two-phase region. So just draw the three lines. Okay, and at point B, right, this is grain boundary. Okay, in similar fashion as we have discussed earlier, here the heterogeneous nucleation will form at the grain boundary. This will be what, so you guys see, we are discussing this for hyper we are discussing this for hypereutectoid steel. Okay, so here gamma is present in whole domain as a matrix, and here Fe3C will start nucleating at the grain boundary. So this is what Fe3C this forms at grain boundary. So this is also called proeutectoid. What Fe3C is what cementite, proeutectoid cementite. Okay, so this is point B. Now let's see for what is happening for point C. So again draw a circle, right, and just draw three rectangles. As we have drawn in earlier case. Okay, अच्छा नहीं बना यार. So here these nucleations will grow Here these nucleations will grow, and in the remaining regions we will get austenite phase. Okay, so this is Fe3C. Fe3C, this is called green boundary network of Fe3C. Okay, and this Fe3C is pro-eutectoid cementite, and this phase is gamma austenite. Okay, so this is for point C. Point C is just above eutectoid point or eutectoid line. Right now let's explore for microstructure for point D. So what is going to happen? First, draw a circle and what is going to happen? This region will grow, this central region of pro-eutectoid cementite Fe3C. This is what pro-eutectoid cementite. Just write it full form in your copy. Pro-eutectoid cementite, and other what we will get alternate lamella. This is Fe3C, और यहाँ पे we will get alternate layer of alpha and Fe3C. So this will be alpha layer. These alternate layers are called perlite. this is Fe3C, this is what alpha, this is what alpha, and so this is alpha plus Fe3C, this will called perlite, this will be called perlite. So this is perlite. So some important observation for hypereutectoid steel, right? So in steel, generally the weight percentage of carbon is greater than 0.8 and it is less than 1.2 weight percentage. In 1.2 it is less than 1.2 weight percentage, right? And what is happening above 1.2 weight percentage of carbon, in steel, so what will be happen? So this Fe3C phase will form more, and hence the steel becomes brittle in nature, and the steel becomes brittle in nature. So this is all about microstructure evolution for hypoeutectoid steel. So this is all for today.